All right, guys, welcome back. This is going to be the 8.5 instructional video. And to kick things off, I want you to do the following tasks. I want you to do three things here. Okay, so on your own, on your piece of paper that you're taking notes on, I would like you to write out 5 to the 6th, write out 5 squared, and simplify the fraction 2 times 3 over 2. So go ahead and pause the video, do that on your own. Well, hopefully these are tasks that you are pretty easy to you. These are things we've talked about that you hopefully should know how to do. So to write out 5 to the 6th, we need to understand what the exponent means, which is 6 5s multiplied together, like so. Same logic, 5 squared is 2 5s multiplied together. And you could have thought about simplifying the fraction a couple ways. You could have said, well, 2 times 3 is 6. 6 divided by 2 is 3. And while that is the correct answer, I think the easier way to think about it is when we have a fraction and we have the same thing on the top and the bottom, the same number on the top and the bottom, and everything on the top and the bottom is multiplied together, divided. In other words, there's no addition happening on the top, right? We don't have 2 plus 3 divided by 2. Okay, that would make things a little bit more complex. But when everything's connected by multiplication or division, and you have the same thing on the top and the bottom of the fraction, they simply cancel. Okay, and again, you can see that by fleshing that out and doing 2 times 3 is 6. 6 divided by 2 is 3. Or again, the shortcut, canceling them out. Again, we can do that as long as there is no addition in the numerator or denominator. Okay? So hopefully those are fairly simple tasks. Now what I want you to do is to combine all of those ideas, and I want you to solve the following for me. Or rather, probably I don't need necessarily the solution, but at least simplify the following. So go ahead and try that on your own. Well, hopefully you've given it a shot, and hopefully, again, you just use the logic we applied above, right? The top, 5 to the 6, can be rewritten as 5 6s, or excuse me, 5 6s, 6 5s all multiplied together. 5 squared can be rewritten as 2 5s multiplied together. And then again, when everything is connected on top by multiplication and bottom by multiplication, assuming we have multiple quantities on the top and the bottom, and they are being divided with that same thing on the top and the bottom, we can cancel out. And this leaves us with 5 to the 4th power. 5 to the 4th power, which we could write out as 625, I believe is what that comes out to be. Okay? But again, what you've noticed we've done, and hopefully if you've been following along in the initial Chapter 8 video series, you know we're working with exponents. You know we're learning exponent rules. You know we're simplifying algebraic expressions involving exponents. And so hopefully you sit there and go, okay, 5 to the 4th is the answer to 5 to the 6th divided by 5 squared. But what we typically do with these exponent rules is we go, is there an easier way to think about it? Right? Every time I have a division involving, anytime I have a fraction, anytime I'm dividing involving exponents, I don't want to have to write them out and then see what cancels. And hopefully, as we've seen in previous videos, you can see a potential shortcut, right? If we look just at the initial part and to our answer, we notice, wait a minute, I have 5 to the 6 on top, 5 squared in the denominator, and I end up with 5 to the 4th. Hey, that exponent of 4 is just the subtraction 6 minus 2. Maybe we look at one more example to really make sure this is a correct rule. Maybe we do 2 to the 3rd over 2 to the 2nd. And by this little, excuse me, shortcut we've observed, if we just subtract the denominator from the numerator, I should end up with 2 to the 1st power here. So let's write it out and make sure that indeed happens. 2 to the third is 3 2's multiplied together. 2 squared is 2 2's multiplied together. We can cancel out 2 of the 2's on the top and the bottom, and that does leave us with just 1 2, aka 2 to the first. And this is going to be our exponent rule for when we are dividing quantities that have like bases. When two values are being divided and have the same base, you are simply going to simplify them by subtracting their exponents, okay? And hopefully you see a relationship between 8.3 and 8.5 here. And that 8.5 is really just the opposite of 8.3. If we think about subtraction being the opposite of addition and division being the opposite of multiplication. In 8.3, you learned, hey, if I have like bases multiplied together, I add the exponents. So in this case, m plus n would be our exponent for our base a. Well, if you replace the multiplication with its opposite, division, you're going to get your 8.5 rule and your addition with subtraction. If I have a to the m divided by a to the n, so I have like bases divided, you are simply going to subtract the exponents. Specifically, your denominator will be subtracted from your numerator. So this rule, while using some different words, it possesses almost the same idea as one of our previous rules. Now let's look at some examples together. Let's say I have a to the 6th over a to the 14th. A to the 6th over a to the 14th. Well, again, we know that if we forgot a rule, we didn't know what we were doing, we could write this out and solve. We do have this new rule that we can apply to solve this problem quickly, or to simplify it quickly, right? We don't know what a is, so we can't technically evaluate or solve it, per se. When I have like bases, which I do here, I have a's, I subtract the exponents and I end up with a to the negative 8th, right? 6 minus 14. You're always going to take away your denominator from your numerator. 6 minus 14, and I end up with a to the negative 8th. But I'm not going to stop there. We always rewrite our negative exponents as positive exponents. And so your simplification would turn into 1 over a to the 8th. And you may notice that I wrote a little hint up here, and I didn't really address it earlier because I think the best place to address it is once you've seen an example. And what this hint would be is whatever side of the fraction has the larger power, the variable ends up staying there. So when we're applying this exponent rule with division, when we have values with the same base being divided from one another, we can subtract their exponents. When we're applying this rule, it's a good thing to remember that whatever side of the fraction has the larger power, the variable will end up staying there. What do I mean by that? Well, if we look at this example we just did, we notice right off the bat the larger power for a is in the denominator, right? We have an a in the numerator and an a in the denominator, but the a in the denominator has the bigger exponent. Consequently, where does the a variable end up when we simplify it? In the denominator, right? So wherever that larger power is, if you have the same base in the numerator and the denominator, that is where the base will end up being when you simplify your algebraic expression. Okay, so it's a good check for yourself. Make sure you're solving it correctly. Let's look at another example here. C to the negative first over d, or times d to the third. And we have c to the fifth, d to the negative fourth. And again, what I have here is I have a product in the numerator, product in the denominator. They are being divided. You're producting your numerator divided by your product in your denominator. Because there's no addition happening in the numerator or denominator or subtraction, what I can do is I can simplify using my exponent rule. And again, for the record, in Algebra 1, we're not really going to see problems that have addition in the numerator and denominator. That'll come in later math courses. So what I see here is I see multiple bases, but each has a like base on the opposite side of the fraction. So where I'm going to start is I'm going to do c to the negative 1 over c to the 5th. If I do negative 1 minus 5, I get c to the negative 6th. I do 3 minus negative 4 for the d variable, and I get d to the 7th power, right? Again, if you write that out, you quickly see that you have a minus a negative, which does create that positive, which we've talked about in previous videos. And finally, again, I want to simplify my negative exponents. So I rewrite this as d to the 7th over c to the 6th. D to the 7th over c to the 6th. And again, I would point you back to the hint that we just discussed, right? Wherever the larger exponent is, when you have like variables being, or like bases being divided, that is where the variable will end up being when you simplify, right? When we look at c to the negative 1st and c to the 5th, the c to the 5th is larger. Consequently, your c variable, when simplified, ends up in the denominator. Your d variable, however, has a larger exponent in the numerator, and so your d variable ends up being in the numerator. So hopefully you use that hint to check yourself. Let's solve this one. Okay, and this one looks a little bit weird. Okay, we haven't really seen a problem like this before. And as we typically do with exponents, when we haven't seen something before, when we haven't seen it before, to maybe before we jump to a shortcut, we identify what's happening and see if there is a potential shortcut we can take. So what does it mean when I have x divided by y to the 3rd power? Well, that means I have 3x over y's multiplied together. X over y times x over y times x over y. And we know from our middle school days, 5th, 6th grade, that when we have fractions multiplied, we multiply numerator by numerator and denominator by denominator. And I get x cubed over y cubed, right? I have 3 x's multiplied together, x cubed, 3 y's multiplied together, y cubed. And now that we kind of see our solution in our initial problem, it becomes very clear all we really need to do is distribute that exponent. And really, these are a lot like the problems we saw some in 8.4, right? When I had a product to a power, I did apply my power to a power rule, but I made sure I applied it to each item in the product. So I'd end up with x to the 3rd, y to the 3rd. The same thing is here, or is happening here when you have a quotient to a power. When I have a quotient to a power, again, you're going to apply those power to a power rules, but you just need to ensure that each item in the numerator and denominator of your quotient, of your fraction, gets that exponent distributed to it. Maybe a couple more examples will help clarify that concept. Let's do 4 over, actually no, let's do t to the 7th over 2 cubed squared and 3 over 5 to the negative 2nd. Again, if you feel good about these, go ahead and try them on your own. Go ahead and try them on your own. So solving the one up top, again, the shortcut we just learned, when we have a quotient to a power, we just make sure each item in the numerator and denominator gets the exponent distributed to it. So what we can do here is we see that we have t to the 7th over 2 cubed. And so we would get t to the 14th over 2 to the 6th after we distribute that exponent. We can simplify 2 to the 6th. That's 6 2's multiplied together. And that will give us 64. Now, an alternate way of thinking about it, and again, we've talked about this before, as we get into the more complex algebraic expressions where we're trying to simplify using exponent rules, there are multiple different ways to think about solving or evaluating or simplifying, depending on what you're doing. Right? In this one, maybe you go ahead and you say, wait a minute, before I distribute that exponent, why don't I go ahead and simplify 2 to the third power? I know what that turns out to be. It turns out to be 8. And if you do that first, you again are still going to end up with the same result. You're just going to get t to the 14th over 8 squared instead of 2 to the 6th. And again, both of those turn out to be 64. So there are going to be multiple different ways you can use your exponent rules to simplify problems. I don't care what method you go about it. I just ask that you use, obviously, the rules correctly. So looking at this one, again, use your exponent rules. Distribute that -2 to each part of your quotient. And when we do this, we need to rewrite our negative exponents as positive. So I simply flip the side of the fraction they're on. Again, that's a topic we learned about in 8.1. We rewrite negative exponents by flipping the side of the fraction they're on. And then we simplify and we get 25 over 9. 25 over 9. Now, an alternate way of thinking about this problem would be, we did learn, again, I just referenced this in 8.1, that when you have a negative exponent, if you flip the fraction, it will make the exponents positive. You can apply that concept when you have a quotient to a negative exponent. Let me illustrate that for you here. We have a -2 as our exponent. If you flip the quotient, and you can rewrite the exponent as positive. If you flip the quotient, you can rewrite the exponent as positive. I'm not going to go use the full definition of the 8.1 rule where we write things over 1 to prove to you why this is true, though if you would like to see that, contact me. And then, of course, if you distribute, you're going to end up in the exact same place we did in the problem above, and you will end up with the same solution. So again, as you see this, you can see there are multiple different ways of thinking through these problems. I don't have a preference. I just ask that you use the rules correctly. Again, my personal preference would be just to distribute the -2 to both parts of the quotient, then flip. But if you would like to flip the initial quotient so that you don't have to distribute a negative exponent, that is an alternate way of doing things. Let's look at 2 more examples, and we really want to make sure you get these here. So if you haven't been trying any on your own, I would encourage you to do so. So I'm going to start this problem by distributing that negative exponent. And when we distribute the negative exponent, especially if we have a negative base, we always want to make sure we put that negative base in parentheses, right? The idea here is that -2 is being put to the -4th power, not 2 to the -4th power and then having a negative multiplied out front. Again, we want that first idea, so we want to put the whole -2 in parentheses. If that's confusing to you, you're more than welcome to come talk to me about it sometime. Then we have x to the -4th and y to the -4th. Again, I start by distributing the exponent to each item in the quotient, okay? Again, probably a good thing to do would be to write 1s for the exponents here. That way I don't mistakenly do -4 times -2 and get +8, right? We're multiplying the exponents by the power to a power concept, not by the bases. We don't do exponent times base. I have a lot of negative exponents here, and since they're all negative, anything with a negative exponent, I'm going to flip to the opposite side of the fraction, which in this case will be everything. And then finally, I can simplify -2 to the fourth. That is 4 -2's multiplied together, which will give us positive 16. 4 -2's multiplied together gives us positive 16. And again, I could have solved this a bit of a different way, right? I could have flipped the quotient initially, and that would have made my exponent of -4 positive 4, and you still would get the same result. Let's look at one more example together. Two AB to the sixth divided by A cubed B. And that whole quantity will go to the -2nd power. Looks very, very complex, but again, you just have more items in your quotient, right? We have a division here of multiple like bases. Everything in the numerator is connected with multiplication. Everything in the denominator is connected with multiplication. So simply what I'm going to do is I'm going to start by distributing that exponent to every item in the quotient. And again, I think a good thing to do would be write exponents of 1 where we don't see exponents. So we do our power to a power correctly. And what this will give me is 2 to the -2nd power. And I'll just put that in parentheses for good practice, even though that base 2 is not negative. A to the -2nd, B to the -12th, A to the -6th, B to the -2nd. And what I'm going to do at this point is I'm going to go ahead and take every quantity that has a negative exponent and flip the side of the fraction it is on. So I will end up with A to the 6th, B to the 2nd, 2 to the 2nd, A to the 2nd, B to the 12th. And when I look here, I see an easy simplification, and I won't even write a new line for it. I'll go ahead and do that now. We know 2 squared is 4. And now we still can do further simplification. Why? Because what we see here is we have like bases being divided, so we can subtract the exponents, okay? And again, remember our little hint. When I look at this, I see that the A has the larger power in the numerator, so my answer should end up with A in the numerator. B has the larger power in the denominator, and so B should end up being in the denominator. So let's do this. A to the 6th over A to the 2nd gives me A to the 4th. And when you do subtraction, right, we're not really messing with this 4 that came from the 2 squared right now. When you do subtraction, automatically you will put your result in the numerator, okay? So I do A to the 6th over A to the 2nd, subtract those, and I get A to the 4th. That will go in the numerator. When I do B to the 2nd over B to the 12th, 2 minus 12, I get -10. But again, whenever I do that subtraction, if I already have a fraction, the subtraction will automatically put that in the numerator. Now what I'll do is I'll simplify the negative exponent, which the B has. Again, I'm not moving the A to the 4th or the 4 because they don't have negative exponents. And I end up with A to the 4th over 4 times B to the 10th. An alternate way of thinking about this, okay, so again, pause the video and copy this down. An alternate way of thinking about this sorry about that. An alternate way of thinking about this would be to simplify within your parentheses off the bat. How could we do that? Well, the 2 to the first would just be alone, but we could do a to the first over a to the third gives us a to the negative second. B to the 6 over b to the first gives us b to the fifth. Again, like basis divided, subtract the exponents. You can handle that off the bat. And then you go ahead and distribute. Might make your life a little bit easier. Again, it just depends on who you are. And we get 2 to the negative second, a to the fourth, b to the negative 10th. And again, hopefully you can tell that we're going to end up in the same place. Move my negative exponents to the denominator, and I simplify 2 squared to be 4. So again, different ways of thinking about the problem and solving it. I don't care which way you go about it, okay? I just ask that you follow the exponent rules correctly. To summarize all that we've been talking about, again, just to give you some hints as you go forth and solve the homework practice problems, when you divide 2 exponents with the same base, I would recommend you are going to subtract them. Divide 2 exponents with the same base, you subtract them. Okay, just like when we have 2 bases multiplied, like bases multiplied, you add them. And again, your hint would be when you are initially looking at a quotient where you have like bases in the numerator and denominator, whatever exponent is bigger on the top or the bottom when you're looking at the like bases, that's where the variable will end up being. So if I have a to the fourth over a to the sixth, I have that quotient. The a variable will end up being in the bottom part of the fraction when I simplify that quotient. To rewrite negative exponents, we simply flip the side of the fraction that they are on. That's a concept from 8.1, but good to reiterate. And when you have something in parentheses to an exponent, distribute that exponent to everything in the parentheses using the power to a power concept. And again, I think you saw that illustrated in the examples we did above. Guys, I appreciate you watching. As always, let me know what questions you have.